So, how we doing? The project is due on Friday. Are we all ready for that? Yo, what have you been doing for the last 4 weeks?
What? Um, if you actually want the pairs printed to the screen,
Mm-mm. They just have to be in a prefix because they're going to be too large. The set will be too large to print everything to the screen. So, yeah, that's the prefix I'm going to give you.
Okay.
So that's the location I'm going to store your output.
After.
Yeah.
So does that mean that we don't start the in our actual button?
You can, but I'm not going to look at it. So I'm going to run your code myself and then look at the output from that.
So you want to enter the prefix when you run what it needs to be an input to the script.
So it's an environment variable. I'll show you in a second. I have to.
So are you running our start EMR file or do you have your own?
I have my own. You can include one if you want. I'm gonna make sure the hardware matches mine. Other than that, um, yeah, you can include your own if you want. That's fine. Okay. Also, confession time. We've talked for like the past 9 weeks about Spark. The original class took 6 weeks to talk about Spark, and I'm running out of material right now. So this is the rest of the things I want to talk about are more theoretical and are more disconnected from each other than the past half semester has been. So if we want to go more in depth on certain topics within Spark, you are welcome to bring up ideas you would like to discuss here. Because the rest of this is going to be more freeform. This is a highly experimental semester for this class because we've never used AWS to the extent that we've used it here, and because we cut out like a month and a half's worth of material from the first part of the class. So the other issue is that the APIs that we could extend the class with talking about are all in Java. And I know there's at least half of you who have not used Java before, either because your previous university didn't cover it, or maybe your previous degree wasn't in computer science to begin with, or whatever. And my previous experience with trying to teach new languages in a class has been not good. So, that being said, and this is why we covered like the aggregation states in the more theoretical sense than actually writing code for a custom aggregation state, because you can only really do that in Java or Scala. I mean, I could start teaching you Scala like next week if we want to do that, but I don't think you do. So I can talk a little bit today about Spark tuning and in general how to get better performance with it. Most of the techniques I use there are pretty simple, but other than that, I don't have much left. So, questions? Yeah.
There are a lot of things about AWS clusters that I don't
Perfect. We can talk about those.
not have all of those things on there. I know a few things that I need to do in order to get somebody on, but there are so many. Just,
Perfect. You're giving me something to talk about. Go. What is it?
well, like even when you go to the EMR dashboard,
Yeah.
you're creating a new cluster or floating one. There are so many other things on there that we haven't like addressed that I'm like, oh, okay, well, I don't know what all these things are. first of all, why? Like, what is Spark's relationship with Hadoop? And what is AWS's relationship with Hadoop?
So Hadoop is Hadoop is like it's a distributed system software that is separate from Spark and also separate from EMR. So Hadoop um used to have like a not used to, it still has a distributed compute system called MapReduce, and that's actually what EMR stands for, is Elastic MapReduce. Hadoop also um publishes a distributed file system. So basically, you can create files and directories of files in like HDFS or Hadoop distributed file system in a very similar way that we do in S3. And so this class used to use like on-prem infrastructure in the Boise State clusters, like I think it's in the engineering building. So we used to use on-prem stuff for this, like in the engineering building and on site at Boise State. So we used to use those. I talked with Amit and we wanted to use AWS instead because when you have a job somewhere and you're setting up infrastructure, it is much more common for you to be using this than on-prem. So people's habits in industry are shifting from using on-prem Spark and HDFS to using EMR and S3.
Okay, but it kind of looks like EMR is still using Hadoop.
Yes. So you can have HDFS running on EMR. There's nothing stopping you from doing that. So the reason we don't use it is because all of the instant storage that you use. So we have a few storage options, right? We can just place everything in memory, and that has very limited space compared to all the other options. So if we were to only store stuff in memory, then whenever we ran out of memory, we would be done. And there's not very much space in memory. So the other option is, per instance, we could store it on local disk. The problem with local disk is that it's ephemeral. So, when we have D-type instances in AWS, like the R6GD2XL that I have you use for your cluster hardware. So that has a disk that's local to it. I'll actually show you. So that has a physical like SSD that's attached to the instance somewhere in an AWS data center that you can access yourself. The problem is anything you store on that local disk is going to be erased when the instance is terminated. And the instances are terminated whenever the cluster is terminated. So that's not long-term storage. Another potential option is to attach EBS volumes to your EC2 instances. That, at least per gigabyte, is an extremely expensive option. So if we look at like oh yeah, that's so expensive. Gigabyte per month. And that doesn't really sound like a lot, but when you compare it to, something like S3 is much cheaper. So if we look at, yes, EBS is persistent. So this is ephemeral. This is ephemeral. This is persistent. And the last option is S3. That's also persistent.
Are the EBS volumes attached to your cluster?
EBS volumes are attached to individual instances. Yeah. So S3 is about a third as expensive, or EBS is about 3 times more expensive per gigabyte than S3 is. And it's less accessible because you can only really attach an EBS volume to a single instance. And there are limits to the size of an EBS volume. I think the limit on the size of an EBS volume is like 128 gigabytes, which compared to the data size that I deal with normally at work is tiny. I deal with data sets regularly that are maybe 5 or 10 times that size. So we can't just store everything in a single EBS volume.
Why do people choose it?
Why do people choose EBS?
Space.
So EBS is a much lower level interface to AWS and its storage that I don't think we've ever actually used just a straight EBS volume. For our storage, at Count, we've used a few different things. We've used Dynamo DB. We've used RDS. What else have we used? Obviously, we use S3. We've used EFS. We've also used Elasticache. So that's like Redis. Has anybody here used Redis before? It's lovely, isn't it? Yeah. And you can kind of separate these things into different classes, right? You would use this for like a real-time database. You would use this for maybe the basis for a data warehouse of some kind. This is just a network file system. Has anybody heard of NFS? So NFS is a protocol that will allow you to share a file system between machines and will automatically sync it for you. So if you have machines that are part of a cluster and you add a file on this machine, that change will automatically propagate to everyone else who mounts that file system. So NFS is a protocol that manages the communication between all of these machines in order to make sure they have the same versions of the same files and to make sure they all have those files. So there are so many different storage options for you. And S3 is our storage option of choice for large volumes of data.
Okay, so Hadoop, AWS is using Hadoop for their EBS volumes?
No, I probably not. Because an EBS volume is just a single entity. Like it doesn't communicate really with other EBS volumes. You would have to manage that communication yourself. So what it could do is you could store part of a distributed file system on an EBS volume. So like the storage might be backed by EBS volumes somewhere, right? But the distributed file system is a protocol that different machines use to communicate with each other on who has what part of the file system.
And when we're talking about that, I'm always imagining that's a memory.
Not necessarily.
But it's not necessary.
No, it doesn't have to be. So it's like with Dynamo. Like this is an extremely simple example, right? And we can talk about what the difference is between the database and the data warehouse. But like data partitioning is a staple of distributed systems because you can't store all of the data on one machine. Like the identity building process that we have at Count, it's like 6 TB. It takes like 6 TB of RAM in order to run. Like we can't store that on a single machine. That's just not possible to do, or at least it's not practical to do. And so we store. That's the entire point of Spark, is so different machines in the cluster can process different bits of the data, right? And so how it works in something like Dynamo or something like Hadoop distributed file system or HDFS is, you have a primary node or a coordinator. I feel like I'm teaching my CS 555 now, which I did teach last year.
Stands apart more.
Well,
Concepts of distributed systems.
that's also an issue I had when teaching distributed systems, is because I kept having to explain concepts that are not actually part of that course's curriculum, but are part of other courses' curricula. So we were in, distributed systems class, but I kept having to explain OS stuff. I kept having to explain stuff like threading and memory management and thread scheduling and all this other crap that doesn't really have anything to do with communication between machines, but is still necessary to understand how an individual node functions. And so what happens is we have, a bunch of nodes, and the responsibility of these nodes is to store a different piece of this distributed file system, right? So like when you store a bunch of files in a prefix in S3, like a bunch of Parquet files in S3, there's no guarantee that each of those files exist on the same machine. Those files are probably on different machines.
But is each file stored as one unit?
Potentially, but potentially not.
Okay.
I don't even think that's defined in S3 because we don't have that level of access. Um, my guess is that I think the maximum size of an S3 object is 5 terabytes. And that's pushing the limit of how big an SSD is going to get. I think. There aren't many SSDs that are that large. Like most of the SSDs for AWS instances, um, even if they have storage that, go past the terabyte range, which they do, it's not that many. I think the largest I've seen is 128 terabytes. I think maybe 64 terabytes. So we're getting there. We're pushing that limit. And so what would happen is, maybe this node stores, 1/4 of the file. This is a horrible. Maybe this node stores, that's not much better, but whatever. We have another. No. This node stores 1/4 of the files. This node stores 1/4 of the files, and so on. And so what Spark does is, when you persist a data frame, you have hopefully every node storing a roughly equal amount of data. And then when you submit code to Spark to execute, like when you use Spark Connect and you say, create this data frame, read, this Parquet file from S3 or whatever, the coordinator will take that, analyze it, using the nodes in here, create a plan, and kind of map out what the execution is going to look like, and then tell each of these nodes what to do with their data. So like if you were to say, let's say you wanted to take the total number of all the words in our Wikipedia data set, right? So that is that's a global aggregation. And, we covered how that works a few weeks ago or a few sessions ago, is every node is going to go through its data set. It's going to create that aggregation state, and then it's going to send the results back up to some kind of coordinator somewhere, which is probably going to be this.
Is that data stored in groups of rows? Or is each are different columns stored?
Oh, that's lovely. Thank you.
Is the data stored on different partitions in groups of rows, or are different columns assigned to different partitions?
That depends on the system. So that's actually a really good example for the difference between a database and a data warehouse. is a database will typically store things row-wise, and a data warehouse will typically store things columnar. So it works like this. So in a database like RDS, which is a normal SQL database. Oh, Christine, is this yours, by the way? Okay.
I keep some on my back. That the first time that professors have taken none of this markers going, so.
Thank you. Okay. So this is just like SQL, a normal SQL database. So this is, something like Postgres or MySQL or MariaDB or whatever. And here is DynamoDB. DynamoDB is a proprietary AWS service. So we don't exactly know what the internals are like, but you can say that it's basically a distributed hash table. But both of these things have something in common. Let's take a look at a SQL database, for example. In a SQL database, things are stored in a SQL database in a row-wise format. So we have column 1, column 2, and column 3. And then in another row, we have column 1, column 2, and column 3. So the difference between a columnar database and a row database is that in a row database, all the columns for a single row are stored together. All the columns for row 1 are stored together, and then after that, all the columns for row 2 are stored together. And so for something like DynamoDB, where different rows can live on different machines, in DynamoDB, if something belongs to the same row, then if two columns belong to the same row, they are in the same place. So that's how things are stored in DynamoDB, is row-wise. So databases are row-wise. Data warehouses. Now, I wouldn't call S3 an example of a data warehouse because it's a little bit too low level for that, in the sense that it's just an object storage. It doesn't really have like any abstraction on top of that. A really good example is Snowflake. How many of you have used Snowflake? Have you used any data warehouse like Redshift or? Okay. So we'll take Snowflake for an example, and I might be able to show you guys our count Snowflake. Maybe. I'll have to ask if that's possible though. Because our security protocols are kind of strict, and I have to promise not to record it or something. But Snowflake is a data warehouse that also uses SQL. So SQL is just a language. It's just a way of expressing how to query a system that holds data. It doesn't necessarily make any guarantees on the performance of certain queries or how the data is structured or anything like that. SQL is just an interface. It defines a way to retrieve data, or it defines what data retrieval looks like to the user. So it's just a syntax, right? And you'll notice that when we perform data frame operations in Spark, a lot of them look exactly like what we would do in Snowflake, except they're named slightly differently. Like if you want to take a data frame and only filter out certain rows that meet a condition, well, that's a where statement in SQL. So data frame operations are directly meant to be analogous to operations in SQL a lot of the time. And things like data frame subtract. Data frame subtract is what's called an anti-join in SQL. So those kinds of things. So our data warehouse, Snowflake, uses SQL to express its queries in the same way that MySQL or PostgreSQL will use SQL to express its queries. But the way its data is structured under the hood is totally different. So data warehouses are usually, but not always, that's not how you spell data. Are what's called columnar format. So that means that instead of rows being stored together, columns are being stored together instead. So we would have, we would have like column 1 from row 1, and then right next to it, we would have column 1 from row 2. And then right next to it, we would have column 1 from row 3. So these are stored together. And then we store column 1 for all the rows continuously. And then when we go to the next column, we store column 2 for all the rows continuously. And then, for column 3, we do it for all the rows continuously. So usually when we're writing code, when we do like maybe object-oriented code, or maybe we want to have our data in some sort of structure, right? Let's say we have our data in a JSON object. That's a row-wise format. We are used to row-wise formats, right? Because we are used to having a single data point, having all the attributes for that data point in the same place. So when we're programming, we are very much used to being able to access all of the pieces of the data when we have that data point. That is not how columnar data warehouses work. So in data warehouses, we have all the data points, but we only have some attributes of those points. And those are stored continuously. Does anyone have any ideas on why things are done this way? Because there's a very good reason.
It seems to me that if you were trying to do like analysis or something with large amounts of data, you're not necessarily as interested in the detail of a row wise. You're probably interested in more aggregations over a whole column. So if I were to store all those together, maybe those things would be faster. So I don't have the shuffles. If my column 3 is storing an amount and I want a sum of that amount, then having that all stored on together on one partition is going to be a lot faster than if I have them spread across 3 different partitions because they're in different rows.
So, kind of. Usually you have many more rows than you do columns, right? So even if you were to extract a single column from all the rows and do analysis on that, you'd still be touching a lot of different partitions because, take like counts omni-score features when we train our machine learning model or do inference on it, right? We have like 100 features for our omni-score machine learning model, and we have a billion rows. And so, if we only have one column, that's 100th of the data because that's only one column, but that's still what, a billion data points right there. That's still a billion different numbers. And so they're probably going to be spread across partitions anyway. So why they do this is when you're writing queries in a data warehouse, this is the part that was right. This is the part of what you said that was right, is that you're only usually interested in certain pieces of the data. Because a lot of the time when you store like raw information, like we store transaction information in our data warehouse. And in this transaction information, we have the timestamp for the transaction and the credit card number and the user's email and the user's phone number, the user's billing address and the user's shipping address. And we have information on their device and what the location is and the IP address and all sorts of other crap. And when we're doing a specific kind of analysis, a lot of the time we only need a few columns, right? Like, what if we wanted to ask the question of, okay, what's the most common email domain for our user base? It's Gmail, spoiler. But it's Gmail. But let's say we wanted to do a ranking. We wanted to know the frequency of, each email domain. If we wanted to do that, we only need to access one column. So even though we need to access multiple partitions, we still need to scan way less data because we're only scanning one column because they're all stored because everything in the same column is stored together. If we were to access a row-wise format, all the other columns are useless, but we'd still have to scan them in to memory. So that's why we use a columnar format for data warehouses, is because when we only need to access a particular column, since all the rows for that column are stored continuously, it's much easier to separate them out when we actually have to do the scan of the data on disk. So that's way simpler. That's way simpler to do. Because this is going to be how it's laid out in memory, right? How it's going to, or on disk. How it's going to be laid out on disk in a row-wise format is I should actually do this demonstration on here. So it's easier to see. And for posterity, because I'm recording my screen, but not this. Okay, so let's say, we have a bunch of rows and our rows are, we're talking about shirts again. So we have color and price. We have blue, and the price of a blue shirt is $15. And then the price of a green shirt is $18. And the price of a purple shirt is $200. And this is all the same shirt. And the reason it's more expensive is because it's 50 BC and purple dye is super expensive. And that's why purple is considered regal. I learned that. I don't remember when. Okay, so these are our rows. How they're stored in a row format is pretty straightforward, right? So on disk, we're going to store something like blue, and then followed by the number 15, followed by green, followed by 18, followed by purple, if I can spell that right, followed by 200. This is how it's going to look like in a row-wise format on disk, roughly. This is actually pretty similar to how something like protobuf would structure it. Protobuf is very compact, but that's beside the point. A columnar format would store it like this on disk. So a columnar format would be, we'd store blue, green, purple, and then after that, we would store the other column. We would store 15, 18, 200, or something like that. I should put columns in between. And format will usually have some kind of delimiter in the serialized format for everything. Maybe we'll put a pipe that says we're separating columns. There we go. Okay, so a columnar format will look like that. And a row-wise format will look like that, roughly speaking. So in a data warehouse, if we only wanted to use a particular column, we would only have to scan this subset of the file, right? This part. We can ignore the other part because we're not actually including the other column in our query at all, so we can just skip it. That's nice. If we were to do so in a row-wise format, things are different because in order to get the values blue and get the value green and get the value purple, we have to scan this entire thing. Because a lot of the time when you access something on disk, the operating system won't allow you to get like super, super granular with the kinds of things that you access. I don't know if this is getting too low level. This might be part of the OS class. Want me to talk about that? Do you want to talk about page faults? Because I could. And it would be interesting. I'll take that as a no. Okay. Okay. So we use columnar formats for this. And columnar formats are kind of counterintuitive because we don't store things in our brain in columnar format. Like we like in our list of data points, we store them in row-wise format, and that automatically makes sense to us. If I were to store this by default in columnar format, you'd look at me like I was an alien. Like, what are you doing? Why are you doing it this way? But it turns out that columnar format can be very efficient, especially when you're dealing with variable length data, because it lets you pack things, lets you pack stuff together in a way that you may not necessarily be able to do in a row-wise format. So we've explained why columnar formats are really useful for data warehouses. Let's look at the other question, the other side of the equation. Why are row-wise formats good for a database?
The packing.
Yeah.
If I have variable format, then it would mess up how I would know which of these go with which. I mean, like I have to know, there have to only be 3 and 3, well, whatever and whatever, so that I know that that blue goes with that 15, green goes with that 18, and that purple goes with that 200.
Yes. So if something is fixed length, like especially in the columnar format, if something is fixed length, even in a row-wise format, this holds too. If a column is fixed length, that makes it much easier to seek out that exact value in a file.
The columns themselves.
Yeah, like the values. Because like when you're programming in Java or C or C++ or whatever your favorite systems programming language is, when you have like an integer data type, it can be different sizes. Like Java has um what's it called? Char. Is that what they call it? They call it char or byte. So char is a 8-bit integer, and then you have a short, which is 16 bits, and then you have an int, which is 32, and you have a long, which is 64. And so if you have that data type, no matter what the value is of that data of that data, um, the length of the actual data type is exactly the same. So if you had a variable of the long data type, and long is actually a data type in Spark too. So Spark inherits a lot of the data types from Java because it's written in Java. So we have a long type, which represents an 8-byte signed integer. So regardless of what the value of that number is, it still takes up 8 bytes in memory. And the same thing for integers. Regardless of what the actual value for that number is, it still takes up 4 bytes. So even if the value is 1, everything else after it, like the next 3 or 7 bytes after that, are zeros. Does that make sense? And so one of the reasons for that is, this is getting into the compilers class, is that compilers need like fixed length. They need to be able to predict the length of the data type. But again, that's not something that's relevant here. The similar concept, though, is that when you have a fixed length data type in a file, like a string is not a fixed length data type, right? It can have different lengths to it. A long is always going to be 8 bytes. So that means you can basically treat your file like an array. So you want to say, I want to get the 16th row, of this column. Then you take the section of the file, which is literally just an array of bytes. You take the section of the file that belongs to that column, take the index, which is 16, multiply that by 8, which is the size of the data type, and then you get the index in the file. You can't do that with a string. And you can't do that with a string because every single row might be a different length. Blue is a different length from green, which is a different length from purple. And so just because you know the index that you want to access something in, that doesn't necessarily allow you to just skip forward to an arbitrary point in the file. That got a little bit off topic.
So this helps with those variable because our data all together, so we're not trying to skip through the file looking for the data.
Yeah.
So it's fine if it's different lengths because it's our column data.
Well, it's also fine. It's also fine if it's different lengths because it's all stored contiguously, and if you're accessing the entire column, you need to access it all anyway. So now we have an understanding, right, of why data warehouses use columnar format. This makes good sense when you only need to access one column. It's to store the entire column together. Why would we use a row format? Like in a database.
And your rows are representing an entity and you're wanting to join to other rows, like when you're wanting those entities to be together, that makes sense to me. I don't know, in my head, those are whole, like we're wanting all of that data to be together.
Well, like Spark, I believe stores everything row-wise. Like in memory, it stores everything row-wise, and that's fine. But for a database like MySQL is used to, serve web applications, right? And its purpose is to store data in such a way where you don't necessarily have to process the thing in batch, but when you make a request to a database, you want a response quickly. Snowflake, it's the opposite end of the spectrum. So, like, databases prioritize low latency in their queries. So they want quick response time. Data warehouses prioritize throughput in their queries. They want to be able to analyze as much data in as little time as possible. And those two things are different, right? Because we know that Spark is an incredibly high throughput system. You can put billions of rows through a Spark process and wind up with decent performance. You would not use Spark to respond to web requests because you have to start up an EMR cluster, which takes 5 minutes, and then you have to start up Spark, which takes another few seconds, and then you actually have to load all the data from S3, which takes some more time, and then you have to do the computation and then give a result. So you wouldn't use Spark to serve web requests that way because the latency is too high. And because generally speaking, a web request will only want a certain small amount of data. But processing little bits of data with low latency is not what data warehouses are built for, which is why for something like Snowflake, even though it can process huge amounts of data, like terabytes of data, we don't use it as a SQL database for web services because it serves a completely different purpose from a data warehouse. So the question is, in a database, like in MySQL, we store things row-wise. Why do we do that?
That's how we're saving and processing. That's how we're getting the information, right? A database is actually gathering, getting some sort of input from somebody, and it's getting all from the web page or whatever. It's getting a row amount of information
Yes.
at a time.
Our access patterns for a database or for real-time services are usually fundamentally different. Like if I'm a user and I want to sign into gmail.com, I want Gmail to have all of my information brought out to me. If we were to do it in a columnar format, what we would have to do is because now for servicing just me, for just my incredibly small amount of data compared to Google's massive data set, they only have to look at a teeny tiny section of a single file. So they know which file I'm in, and they can go look for me within the file with, some kind of search algorithm within the file they have. Maybe the file is sorted by my username or whatever, and they can use binary search or something. But we only have to access a single part of a single file. If we were to try and access my information from a columnar format, we would have to look at the section for one of my attributes, which is my username, look at a different section of the file in a completely other part of the file for maybe my password salt so that they can authenticate me. Maybe we have a third column somewhere in a completely different part of the file somewhere else that stores information on my mailbox. And we'd have to look in a completely different part of the file to look at that information. So usually, if you want to access a single row's worth of information, and that row is pretty small, you would want to use a row-wise format. So whether you want to use this format or this format depends on your access patterns. It depends on what you're doing with the data. So that's why databases and data warehouse are designed in fundamentally different ways because they serve different purposes. And this is an example of the different design decisions that they've made and why they've made it. And so in addition to SQL, DynamoDB, which is a distributed database, it's basically a hash table. Yeah.
So if I understand like storing like a username and an email and a password relies because that's how it's like access. But if you stored it columnar, would it make it harder for someone to like get a hold of all of the information for a specific user?
Um, I wouldn't say it's a security improvement to do that because it would make the retrieval slower. So, um, maybe we should talk about page faults. So, a page fault is okay, I won't explain all of it, I promise. So a page fault is when the operating system reads a part of data from a file system, like on disk. They don't read like they don't read only the amount that you want. So um let's say we wanted the second column value of the third row, which is 200, right? What you could do is if all of this data was stored in memory, you could find out the address for that data value, increment the pointer, dereference the pointer, and that's all you would need to do. For a file system, it's different. And for reading from disk, it's different. So when you read in a piece of a file, the operating system will actually take like a 4 kilobyte chunk and read that entire thing into memory. That's called your block size or your page size. And so usually, a lot of the time, a row is not actually that big. You know, like this row is what, 6 bytes or less? And we have to read 4 kilobytes off of disk in order to read just this row. If we wanted to read this information in a columnar format, we'd have to read 3 pages, right? Because probably these two columns from this row are not going to be in the same page if we use a columnar format, right? So we'd have to read this page, this 4 kilobyte block of the file, just to get the blue column. And then we would have to go to a completely different part of the file, maybe 300 or 400 megabytes later, and read in a different part of the file. And when we read in that different part of the file, that's a different page because it's in a different part of the file. So you'd have to read in another 4 kilobyte block. Does that make sense? So in here, we'd only have to read 1 page from disk. In here, we'd have to read as many pages as there are columns from disk. So in terms of the amount of I/O you'd have to do with disk in order to read a single row, this is much more efficient. Make sense? Cool. I'm just explaining things. I'm not sure if or when or why I would test you on this, but we're having fun.
Okay, so can any of these storage things in any of these storage types, they all can be done distributed. Like all the databases can be distributed, the data warehouses can be distributed, your caches can be distributed, everything, all of these storage things we've talked about can be distributed.
Yes. So Snowflake is a distributed system and they use columnar format. DynamoDB is a distributed system and it uses row-wise format. So I can actually just create a Dynamo table. That sounds fun. Let's do that. Let's create a Dynamo table.
Space for a dynamo table. Why does it choose?
I'm about to show you. I did not develop any material to talk about DynamoDB. This is ad hoc. It doesn't use SQL.
Because then you just can't query it.
I mean, so like, I don't really understand the terminology of NoSQL because I think most people's understanding of NoSQL is it doesn't allow like complicated database transactions. So you know the ACID transactions in a SQL database, what's ACID stand for? It's atomicity, consistency, isolation, durability. Is that what it stands for? I think there's another thing.
Yeah.
Huh? I remember 410 from 5 years ago. Okay. There's also base. Oh, how do I word this? Base, there we go. Base acronym data. So there's an ACID database and a base database. Like, did anyone know that base databases exist for this? This is so funny. I love how they created an acronym just so we could be the opposite of ACID. I find this hilarious. Okay. So most like a traditional SQL database like Postgres or MySQL is going to be ACID compliant. So it will allow you to create transactions which are atomic in the sense that they execute as a single unit. Either the entire thing executes or nothing does. The consistency part is when you execute a transaction, and the transaction affects certain constraints on the table. So let's say you have a foreign key constraint on one of your tables, and the foreign key constraint is set to delete cascade on your table, which basically means that if I have a person in a database and I have a foreign key that refers to the person table and I delete the person from the database, I also delete anything with that foreign key. So that's the cascading update. So the consistency part is making sure that those constraints hold all the time, every time. That's the consistency part. Isolation, what does that mean? It's been a while. Oh, I mean, that just sounds like atomicity, honestly. Isolation ensures that concurrent transactions do not interfere with each other. That just sounds like atomicity. It sounds like an extension of atomicity. In fact, when you want an operation to be, self-contained and concurrently consistent, we call that atomic. There are special CPU instructions that allow you to increment like whatchamacallit, an integer variable with a single instruction instead of what three like you would normally have to do, and they are called atomic instructions. So I don't really understand why this is called isolation. It just sounds like atomicity.
Can't change the same record at the same time. One locks it.
Well, yeah.
the way Google Docs works, right? Like,
Well, yeah, Google Docs is the total opposite. I'm pretty sure they use CRDTs, which are insanely cool, but we can't talk about them because this isn't the distributed systems class.
I mean, that the idea that that doesn't allow for that. We can't both be altering a record at the same time.
Well, yeah, but that just sounds like atomicity. Because that's what atomic instructions prevent. So like in atomic instruction, if you had one thread on a process and you're trying to increment an integer variable, and you have another thread in the same process and you're trying to increment the same variable, what you would have to like let's say we're executing in parallel because executing serially doesn't really matter here. We're executing in parallel. What your processor has to do is it has to read from memory, reach into memory, and take the value into your core registers, into the register for your processor, do the increment, and then store it again. It works the exact same way in a database, right? If you want to change a value, a lot of the time in a database, you can't store something in place. You can't do the update in place. If you wanted to increment a value in a database, you have to read it from the database, do the addition, and then store it again. That is a non-atomic operation because you're actually doing three things and it's not just one. It's divisible into three separate interactions, right? An atomic operation is a single interaction. So it'll basically do the read from the database, the increment, and the store to the database all at the same time, indivisibly, so that you don't have multiple writes interfere with each other. Because what could happen is if you have two people who are trying to change the same variable at the same time, let's say we're trying to both increment it by one, we could both read at the same time, and then at the same time do our increment on our end, and then do a write to the same place at the same time. That means one of the updates is going to get lost. Those are consistency issues. We talk about those all the time in distributed systems. We cannot go into more detail here because that is an entire semester worth of stuff.
And that's something that Spark is managing.
Yep. So in a distributed system, transactions are much harder to manage, and a lot of the time they just straight up don't exist.
What doesn't exist?
Transactions. You most of the time can't do transactions in a distributed system because the coordination is really hard to manage.
So if you had a really smart database,
Mm-hmm.
just you're saying you couldn't do it distributed, you just need to offload your records and small so you don't want to distribute it.
Well, your constraints just wouldn't be enforced. So a really good example is again Snowflake. Or in key overview of constraints. Where did it go? Okay, here we go. We're not going to talk about hybrid tables because those are a beta feature in Snowflake. So in a standard Snowflake table, primary key constraints are not enforced. So even if you declare a column to be a primary key in Snowflake, if you insert another row into a table in Snowflake with a primary key that already exists, it will not prevent you from doing so. So the primary key constraint is not enforced at all. The same thing with foreign key constraints. If you have a column in a Snowflake table that is meant to refer to a row in another table or another row in the same table, and it has that identifier, it does not go to the other table and make sure that that identifier exists. The foreign key constraint is not enforced in Snowflake because those are part of transactions. Those are part of the transactional nature of a traditional SQL database. Those features are not present in most distributed databases.
Okay, and that makes sense from a data warehouse point of view.
Okay.
Right? When I think about how long it took you to read in Wikipedia, because it was trying to make sure that keys were enforced.
Yes.
Right? That makes sense.
Yes, that took forever.
But so your data warehouse stores transactions, but like our transactions, then we're assuming that those constraints were held in the database it's coming from, or like otherwise it doesn't do us any good to have a data warehouse full of junk.
I mean, but we have data warehouses full of junk all the time.
Well, that's a problem.
Yes, it is. But computationally, like we don't have the capacity to handle that sort of thing in a warehouse like this.
Okay, so let's say you have 1 million transactions a day
Okay.
and you're dumping those transactions into your warehouse.
Yep.
You could have your actual working database be offloading those transactions and therefore be having a small enough transaction that it doesn't have to be distributed. And it could enforce the keys as it's creating these transactions.
Well, sure, that's the motivation for using a SQL database in this day and age, right? A lot of people are saying, "Oh, you should move to NoSQL because it's so much more scalable and it's so much better." And it's like, wait, hold up, hold up. The reason we like SQL is because it enforces all of these constraints for us. So if you don't need the scalability of a NoSQL database, don't use it.
So could you just not increase the frequency with which you offload your transactions if you need it scaled?
I mean,
Or is that impractical?
could you increase?
Let's say you were like, look, we want to enforce data integrity.
Okay.
And so we want to have the actual real time in an actual SQL database that enforces our data rules. But we're having way too many transactions to even go a whole day without, to have those in there. Could you not offload those transactions every hour to your data warehouse to keep the size of your SQL database small enough? So that when you're creating those transactions, it's still enforcing all your rules?
I mean, sure, but in order to force the primary key constraint globally, you'd still have to store all of your rows that you've ever gotten.
Oh yeah, you're right. Oh yeah. That's.
So that's disappointing, right? Is that you have to make your choice between your constraints being enforced and your data integrity. You have to make that choice as a trade-off with your data volume. And we made that choice at count. We decided our data volume was too large to justify or to use a table or a technology with a foreign key constraint. So we decided to use a standard Snowflake table, which is high performance and doesn't have anywhere near the same kind of validation.
Okay, so what is Hadoop doing?
Huh?
I also know.
Which part?
Hadoop.
Oh, okay.
Who is Hadoop?
Who is Hadoop? So Hadoop is the software that manages the distributed file system. A hypothetical distributed file system that doesn't exist because we use S3.
Okay, so if we don't select that to use Hadoop when we spin up our cluster, we'll be just fine. With those checklists.
I think we still need it. Spark might use some other like lower level primitives from Hadoop. But we don't need anything that's explicitly like from Hadoop because we don't use Hadoop MapReduce and we don't use HDFS. Hadoop might also have other things like cluster management or IO streaming that Spark might make use of. Like I said, lower level APIs, but anything I've used to program directly with Hadoop, we're not going to be using. But Hadoop might still have like interdependencies and primitives that Spark might want to use, which is why it's included.
So does S3 have its own Hadoop counterpart to manage its distributed file system?
Yes. Yes, it does.
Does it have a name? Or is it just comes with it once you use S3, just notes it?
Well, S3 is the proprietary service, so all we have access to is its interface. And without like reading the source code or internal architecture documents from Amazon, I can't tell you.
Okay. And there are other things on that list too, like what's Hive?
Hive is a data warehouse system that you can use that's backed by HDFS. So Hive is like this data warehouse interface that's similar to Snowflake. So you can create SQL tables and execute SQL statements and stuff like that. It works a lot like Snowflake in the sense that it looks like a database, it operates like a data warehouse, and all of the data internally could be stored on HDFS.
I think we have that check too. Why are we checking her?
You might not need it. I don't use it.
It's just another thing on the file system.
Well, yeah, so it's not going to hurt you when you have it there. But you could probably uncheck the box and it won't do anything. Probably.
Whereas Livy would be hurting us.
No, you can uncheck Livy. I do.
No, like it was checked, because it's in our instructions to uncheck.
I mean,
That's specific.
it's you have a choice on whether to do so. So if you checked the Livy box, it wouldn't make a difference. You would just start the Livy server and it would sit there feeling sad because it's not doing anything.
Gotcha.
So if you did want to use this HDFS, where are you going to store them? Like if you're using a cluster and we're like, okay, we want to use this HDFS distributed file systems, but we can't do that with S3 because it has its own proprietary. Like, what's our option? Where does that get stored in the file?
I mean, we would have to manage that ourselves. We would have to manage like some kind of intermediary that automatically backs HDFS into S3 or use EBS volumes and back it that way. We'd have to do it ourselves. S3 is much easier. It's managed. That's why I wanted to switch to AWS because I didn't want to spend 4 weeks teaching it HDFS. Only for you to use S3 when you got into industry anyway. Okay. We're almost at time. This was fun. I like seminars. This felt more like a seminar than a lecture.
Well, there are a lot more things on that.
Do you want more seminars?
Yeah.
Okay. I do have to test you on some material at some point.
Yeah, there are other things that you can click when you're starting up. Can you add more things to that, or do you do that through Bootstrap scripts? If you're like, look, I need this, like,
Hold on, what are you asking about?
you start up your cluster, you can check and say, yes, include Hadoop, include Pi, include. I think Lizzie is one of them.
Yes, it is.
Okay. How do those things get in that checklist? And yet if we want other things installed on our cluster, we have to either put in a bootstrap script, or maybe we could do it in the JSON, the config JSON or something.
So that's just what AWS decided were the things that were common enough to include in the box. That's the only difference. So a lot of the other stuff we have in our Bootstrap scripts at count, they're all custom things that AWS doesn't think are common enough to include packaged into it.
Okay. Why do I sometimes have to put them in Bootstrap scripts and sometimes I can put them in that JSON?
What do you mean? Hold on, Christine, did you have a question?
No, I was. I understand AWS is probably the most popular in industry.
Yeah. So we have AWS, GCP, and Azure. Equifax likes to use GCP, and we all love Equifax for that. That was 100% the correct decision to choose GCP over AWS. We don't disagree with that at all. AWS has probably the most comprehensive feature set of all the cloud providers. They also have the biggest market share. Last I heard, they had like 34% of the market share, followed by Azure, which was about 20, followed by GCP, which was about 10.
Where's the rest of the market share?
There are other things like Oracle and Alibaba and HP Enterprise that take up the rest of the crumbs.
cloud service and
I thought AWS had like limit short. And they're both 50.
I don't think so.
I mean, I believe you. It's just funny to think that.
Yeah. What were you asking earlier?
I will go look so that I can speak more into like.
Okay. Bye.
Thank you.
Oh, we didn't create the dynamo table. We'll do that next time. Next time. Hello, user. There's somebody else labeled user.